We are Team A07 and this is our coin picking robot project for ELEC 291. Our battery-powered robot and remote controller combination utilizes two microcontrollers from different families. It operates in two modes. The first, manual, is where the user controls the robot's movements and tasks using an interface on the remote control. The second, automatic, is where the robot moves autonomously within a predefined boundary of 0.5 meters squared, detecting and picking up a total of 20 coins, 4 of each type of Canadian coin currency, including a toonie, loonie, quarter, dime, and nickel. While in these two modes, the LCD display and buzzer on the remote control conveys information to the user sent from the robot about the strength of the detected coins. Here is our hardware block diagram for our remote and robot. In the remote, the LM7805 voltage regulator converts 9 volts from the battery to a stable 5 volts to power the LCD display. This is then further stepped down to 3.3 volts by the MCP1700 low dropout regulator for use by our microcontroller, the STM32, part of the ARM family. From here, it takes analog inputs from the joystick to control robot movements, as well as from a set of voltage divider configured push buttons to convert to manual or automatic mode. The STM32 then outputs a signal to change LED configurations based on the mode. The buzzer is used to audibly signify changes in the metal strength detected. To communicate with the robot, the JDY40 radio is used. The robot is also powered similarly as a remote by 9 volts. On the robot, we use the EFM8 microcontroller, a part of the 8051 family. It takes inputs from the coin detector, the culprit's oscillator, and the other two inductors are used to detect the perimeter, where a 15 kHz square wave is generated through a magnet wire. The values read by this is fed through to an op-amp, the LM358P, to increase the voltage to readable ADC ranges. We also implemented an extra feature, the ultrasonic sensor, that detects standing or hanging obstacles within the boundary. The EFMA outputs signals to the motors, servos, and electromagnet based on radio inputs from the remote. However, these are passed through an optocoupler, the LTV847, which is used to stabilize different grounds for each voltage rail on our breadboard, preventing spikes from noisy components such as the servos to the microcontroller. Signals to the motors are controlled by an H-bridge consisting of an NMOS and PMOS transistor, which allows movement in 4 directions based on which pairs are powered. For the most part, the software logic is based on what state the robot is in, manual or automatic. Upon startup, the EFM8's ADC, UART, LCD, and timers are initialized. The robot then configures the radio connection with the remote, as well as calibrates the base frequency and voltage to ensure highly accurate perimeter and coin detection readings. Starting off in manual mode, the remote and robot loop across a series of steps. The remote sends instructions via the radio to the robot about the analog readings from the joystick and the push button, and it also requests data to display metal strength on the LCD and to change the buzzer frequency. If the joystick is pressed down on, the robot runs through the coin pickup function. If the mode switching button is pressed, the LEDs are complemented and the robot switches to automatic mode. While in automatic, the robot loops again, starting with moving forward and checking if the perimeter or an obstacle is detected. If so, the robot follows a random turn sequence and continues. If a coin is detected, the coin pickup function is called. Then a check for the target number, 20 coins, is reached. If it hasn't, the robot returns to the loop. If it has, it returns back to manual mode and the process repeats. According to the data we collected from testing, the different frequencies generated by each type of coin will cause the buzzer to beep with a certain frequency, representing the proximity the robot is to a toonie, loonie, quarter, dime, and nickel. The strength rating displayed on the LCD is a relative rating from 0 to 100. Here is a demonstration of our robot in automatic mode. It roams around a predefined boundary autonomously until it picks up 20 coins. An extra feature we added includes an ultrasonic sensor that can detect standing or hanging obstacles in the boundary, increasing the difficulty in the robot's movements. Our robot is also excellent at detecting the perimeter with a tank circuit. The voltage output of the peak detector decreases when the inductors get close to the wire, which changes the ADC reading. After picking up 20 coins, the robot returns to manual mode, and the user can control its next movements. A challenge we faced was integrating all the individual components together on the breadboard. We solved this by using a mini breadboard underneath the main one in the body of the car. Additionally, programming with limited memory on the EFM8 microcontroller caused issues with float data types, causing the necessity to optimize our code and memory. Some improvements we can make in the future is the inclusion of a photocell sensor for automatic use of headlights in dark conditions, as well as adding more ultrasonic sensors to detect 360 degrees around the robot rather than just straight ahead to prevent the end of the robot from bumping into any obstacles. Overall, our coin-picking robot is successfully able to be operated manually with a remote as well as automatically within a certain area. Thank you, and we hoped you enjoyed our project.